Hey everyone, my name is Khurram Azim Hashmi and I will present the paper called Spatiotemporal Learnable Proposals for End-to-End Video Object Detection. This work is in collaboration with Didier Stricker and Mohammad Zishan Afzal. The primary task of video object detection is quite similar to still image object detection, in which objects in each video frame need to be localized and classified. However, owing to the frame deterioration problem caused by motion blur, camera defocus, occlusions, and pose variations in videos, applying image-based detectors to solve video object detection lead to unsatisfactory results. To tackle these challenges, modern state-of-the-art video object detection methods take multiple frames from a video as input and apply the region proposal network on each video frame. Once they have region proposals from each frame, they devise effective aggregation schemes that enhance the region proposals of the target frame by exploiting proposals from support frames. Although these modern region-based video object detection methods achieve the enormous success, it is important to highlight that the temporal feature aggregation scheme of all such methods heavily rely on region proposals from a single frame RPN trained without any temporal information. Consequently, these methods suffer from several underlying restrictions. First, they require an additional step of non-maximum suppression at the beginning to perform dense to sparse matching of handcrafted anchors, which makes the overall pipeline not end-to-end optimizable. Second, on low quality frames, the generated object proposals are unreliable, which leads to ineffective temporal feature aggregation as illustrated in subplot A, that although the detector leverages spatiotemporal information from support frames, it fails to detect turtle at the target frame. The main reason for such mispredictions is that generated proposals from single frame RPN overlook turtle in the target frame T. This corrupts object features during instance level feature aggregation. To tackle these limitations, we propose Sparse VOD, an end-to-end trainable framework that exploits temporal information to learn sparse object proposals for video object detection. The proposed sparse VOD framework extends recently introduced sparse RCNN by introducing temporal dynamic head block that iteratively refines the target frame object proposals by leveraging proposals from support frames. Now we dive deeper into the proposed architecture of our sparse VOD. The input for the first stage of the temporal dynamic head consists of initial proposal boxes, proposal features, and spatial features for the target and support frames. While proposal boxes and spatial features are used by the ROI line operation, proposal features will be used later. Once we have the ROI features for support frames, the temporal feature extraction module enhances ROI features for the target frame by aggregating proposal features from support frames. Since the feature of the same object instance have high semantic resemblance across video frames, we compute cosine similarities between target proposal features and support frame feature maps, and then use a multi-head attention block to aggregate them. The enhanced temporal ROI features for the target frame and respective ROI features are fed into their own exclusive instance interactive head, where each head is conditioned on specific proposal features. Then the semantic proposal feature aggregation learns the enhanced feature representation from target ROI features and support frame ROI features prior to final classification and regression. This rich instance representation from SPFA is propagated to each feed-forward network to perform classification and regression. Since the implementation of temporal dynamic head is iterative, the newly generated predicted boxes and enhanced features from SPFA will serve as the proposal boxes and proposal features of the next stage in the iterative process, as highlighted by the red line. After 6 iterations, the final output is computed for the target frame only. Since we are dealing with a sparse, merely 100 proposals, the iterative architecture only introduces a marginal computational overhead. Following the common practice, we use the combination of ImageNet VID and DET datasets to train and evaluate our method on the ImageNet VID validation set. Besides computing the mean average precision at IOU of 0.5 for direct comparison with prior works, we also report results on increasing IOU thresholds. We compare the performance of our method with recent state-of-the-art approaches on all three variants of ResNet 50 backbone networks. The best two results are highlighted with red and blue. By looking at results under the backbone of ResNet 50, it is evident that our sparse VOD surpasses the previous best score of 79.9% by trans VOD and achieves a new best score of 80.3%. When stronger backbones of ResNet 101 and ResNet 101 are incorporated into a method, the performance further increases to 81.9 and 83.1% respectively. Note that although Mamba, Mega, and TROI demonstrate better results at mean average precision 50, our sparse VOD supersedes them by far, approximately 4 to 5 points in mean average precision on higher IOU thresholds. In this ablation, we investigate the impact of adding each component to build our proposed method. Beginning with a single frame baseline, we incorporate the TFE module and boost the AP50 from 71.1% to 76.9%. This demonstrates the benefit of exploiting interframe information to extract ROI proposal features. On the other hand, by separately plugging the SPFA module into a single frame baseline, we achieve substantial gains in AP50 from 71.9 to 79.1%. Finally, by combining both, we gain a further boost of 1.2% in AP50, accomplishing 80.3%. These results establish the superiority of introducing spatio-temporal feature aggregation for learnable proposals. We also show a speed accuracy trade-off between our and previous best region-based methods. With only 6 support frames sampled from the entire video, our method achieves a new AP50 of 80.3% with a runtime of 14.4 frames per second. In contrast, TROI manages to reach its best performance AP50 of 78.8% with a runtime of 7.5 frames per second after utilizing 14 support frames. These results reflect that the temporal feature aggregation from several support frames in prior region-based methods lead to a major increase in runtime, producing a suboptimal speed accuracy trade-off. Contrarily, thanks to the spatiotemporal learnable proposals, our sparse VOD yields an optimal speed accuracy trade-off. We also visualize the behavior of learned proposals and bounding box prediction at different iterative stages from a converged model on the validation set. Note that the learned proposal boxes in part A cover possible regions in all video frames, while the iterative heads in each stage enhance detections. The part T, stage 6, further exhibits the robustness of our sparse VOD by producing high quality final predictions in challenging scenarios involving camera defocus and part occlusions. To conclude, in this work we highlight the important problem in existing region-based video object detection methods that their temporal feature aggregation schemes heavily rely on single-frame RPN. To tackle these challenges, we present the novel idea of generating object proposals while leveraging temporal information. Our sparse VOD eliminates handcrafted dense priors and provides reliable proposal features even with deteriorated input frames. Particularly, the sparse VOD incorporates attention-guided temporal feature extraction and semantic proposal feature aggregation modules in sparse RCNN. Besides achieving state-of-the-art mean average precision on ImageNet VID dataset with ResNet 50 backbone, our method outperforms existing region-based methods by a significant margin on increasing IOU thresholds and yields optimal speed accuracy trade-off. Thanks a lot for your attention.